Uh, Hello. Uh, as you're aware that we were doing s- some concepts in wave mechanics. In today's lecture also, we are going to start with these concepts. Mind you, these are very important concepts, so kindly pay a little bit of attention to all these concepts. At times, there are chances that you may think that probably a few of these things may not come in the exam, but overall, I'll suggest that you should pay much attention onto these concepts. So, without wasting time, let us start. So for this is the as title suggests, I have given the title further concepts in wave mechanics. Okay, and these are some very important concepts that one needs to remember. Till now, I hope we have done some few things. I'll list them up because it has been a while that I've taken the class. So one of the things that we've already done is I think Schrodinger equation. The first thing that we did was Schrodinger equation. No doubt, I have right now not taught you about wave packet and all those things. We'll go through all those things. Don't worry about it. But let us start at first. Let us start at first with some understanding of how to do quantum mechanics. Okay. Uh, as we know that Schrodinger equation for a non-relativistic particle and in one dimension, moving in one dimension, is given by this equation. So, as you're aware, when we do this thing, when we do classical mechanics, or uh, when we do classical mechanics, or let's say statistical mechanics, there are certain laws. Okay, so for example, when we do classical mechanics, we have Newtonian equations. Okay, now for the a particular state of quantum system, you know that a state of quantum system, I'm writing it here. Okay, so I'm writing it here in small, that we understand that a state of quantum system, what should I write? Let's say whether it is a single particle, or whether it is a single particle, or you can say system of particles also. They are described by this wave function. They are described by, you can say, a single valued, you can say in general complex mathematical object called as wave function. And then there are certain conditions on these wave function, that is, for a solution for this particular you can say, let's say, this differential equation, or you can say this Schrodinger equation. If there are certain conditions which are imposed, or you can say which your psi follows. Okay, so there are certain conditions for this psi, and we say that these conditions are quite necessary, and these conditions are for the physical realizability of the solution. Okay, so for a physically acceptable, and a well behaved function, well behaved wave function, What are those conditions? The first condition is somehow this particular wave function psi x should vanish as x tends to plus minus infinity. This is first thing that you should remember. Second thing is that d psi upon dx, it's not necessary that this is continuous. Not necessarily continuous. So there are cases, for example, when I'll teach you the potential, uh, various potentials, and the solution for Schrodinger equation for various potentials, you'll find that there are potentials when let's say Dirac delta function, or okay. So for example, Dirac delta function, let's say if your potential follows this, you'll find that your wave function no longer, the derivative of the wave function no longer remains continuous. But in general, the wave function should remain single valued. Here it is written single valued. It should also be continuous, and it should vanish as x tends to plus minus infinity. This condition is necessary. This condition is necessary because if at all it does not vanish and it, let's say, it goes out of bounds, then it will not be able to define the probability. Will not be able to define the probability. Indeed, one more thing is very much interesting, and one should remember that this should be psi must be square integrable. We'll come to all these technicalities. Probably more mathematics we'll do in the series of linear algebra, but right now just let us focus on physics part. So psi must be square integrable. And why it must be square integrable? Because somehow we know from the max bond probability interpretation of probabilistic interpretation of wave function, we understand that psi mod whole square represents the density of finding the particle between x and x plus dx, and let's say if it is 3 dimension, then tau to d tau, and this particular thing from minus infinity to plus infinity represents the probability of finding the particle from minus infinity to plus infinity. So since probability is a real term and it should be some finite value from 0 to 1, okay, so this particular thing should be square integrable. If this psi is not square integrable, let's say it diverges, then it does not make sense. It does not make sense. So in any case, you should remember that since this particular fellow, that is psi mod whole square dx represents the probability of finding the particle somewhere in the space. Somewhere in the space. So you should remember one very important thing, that this should be finite. Okay, it should not diverge. So psi must be squarely integrable. That is very much sure. Okay, so for example, let us take some examples, and let us see if that goes in your head or something. So let's say if I say that the wave function psi x is represented by let us say a times secant of x. Do you really think that this can form a physically acceptable wave solution for the wave function? Does this psi x is equal to a times secant x कुछ भी feasible नहीं है? Okay, this is difficult. Just give me a minute. Okay. Mm, okay. Let me help. Just give me a minute. I don't know what is the problem. Okay, just give me a minute. Okay. Let me see if it's now visible. Okay, just give me a minute. I think now I think it should be visible. Mm, so let me do something about it. I don't know if it's that visible. Okay, so just wait for a minute. I'll send some other link. Okay, so I think I don't know why it's not working. Okay, I'll send another link. Don't worry.